In the last video, we proved the power rule, but we proved it for power functions, which are where that exponent is a positive integer. So we proved it if n was a positive integer. What's really nice is it is true if n is any real number. Now, we don't have the tools at this point to prove that. I am simply going to tell you that. That is my gift to you. It is actually a gift from the mathematicians that have gone before who have proved that. Okay? So, we derived the formula in certain cases. We are being given that it is true in all cases. Now, what's great about that is that now I can take the derivative of the square root of x using the power rule, because I know that roots can be written as fractional exponents. So what I would want to do is I would want to first of all rewrite that as a power. I would say that's x to the 1/2. So here I'm saying I'm going to take the derivative of this function. Now I haven't taken the derivative yet, so I still have to write that operator. This is the same function, it's just writing it in a form that makes it easier for me to calculate the derivative. Now I can apply the power rule. The power is 1/2, so that comes down and becomes the coefficient, and I multiply that by x to the 1 less power. So it's going to be 1/2 minus 1. Well, 1 is 2/2, so this would be 1/2 x to the negative 1/2. Okay. That is my derivative of the square root function. Now, I can also write that as 1 over 2. Because this exponent is negative, that tells me that power's in the denominator, and because it's a fraction, it tells me it's root x. So these are equivalent formulas for the derivative of the square root function. But that's so much faster than having to take the limit of the slope of the secant line. You are going to need to sometimes take your roots and rewrite them as fractional powers so that you can apply the power rule. Now, the power rule will also allow me to take the derivative of 1 over x squared. It will allow me to take the derivative of reciprocals of powers. Okay. You'll notice I'm using this d by dx notation. It's a huge time saver. Let's just take the derivative of this. If I didn't use that notation, I'd have to say, okay, our function is 1 over x squared. Now calculate the derivative. And to write out those directions takes a whole lot longer than saying, take the derivative of that function. I really like the d by dx notation because even though at first it seems kind of unwieldy, it allows me to say, I'm going to take the derivative of this function. Again, without just writing the function and then in a separate line saying, now let's do the derivative. All right, if I want to apply the power rule applied if I have just x to a power. This is 1 over x to a power, that's different. But I know that when my x's are in the denominator, I could rewrite that as a negative power. So 1 over x squared is the same as x to the negative 2. So that power comes down, we get negative 2, and then it's x to the 1 less power. So that would be negative 2 minus 1. That's going to be negative 2 x to the negative 3. Do be careful here. Okay? When you're working with negative powers, when you subtract 1, you get a bigger negative number. The absolute value of the exponent increases, even though the actual value is decreasing because it's becoming more negative. So a common mistake that I see is people say, oh, 1 less than negative 2, that's negative 1. But it's not. That would be 1 more than negative 2. 1 less than negative 2 is negative 3. Okay. So the power rule is going to allow us to take derivatives of roots, and it's going to allow us to take derivatives of reciprocals of powers, because roots correspond to fractional exponents and reciprocals correspond to negative exponents.